Now, let me share my screen.
Yes.
Hope everyone can see my screen. And my voice is coming, okay? Everything is okay?
Yes, we can see your presentation.
Okay. Can you see my presentation now?
Yes.
Okay. Thank you for introducing me. And before starting my presentation, I would like to thank Professor Felipe and his colleagues for organizing this meeting. Hope I can contribute this meeting. My topic is graphene reinforced composite for aircraft structures. And by the way, this background picture is from our institute. Now, in this slides, I will give some information about some of my ongoing and some completed research project. In the first project, we produced electroactive polymer actuators, and we used the ketosan electrolyte, and this electrolyte sandwich between the two electrode materials. We used the silver dope graphene as electrode materials for this electroactive polymers. This is for artificial muscles. And another actuator process, we use the PVDF-based electrolyte materials, and we coated these polymer with the silver nanowire graphene using the electrophoretic deposition method. In the third project, we produced the hard magnetic materials using the rapid solidification techniques, melt spinning method for hybrids and electrical vehicles. Now I will give some presentation about the graphene added carbon fiber composite. This is also ongoing project, and now I will present the work done up to now about this subject. Composite materials form of two or more materials, and to produce the unique properties that does not have any single materials, does not found in a single materials, and they are commonly composed of the matrix and reinforced materials. The matrix materials should be should be the ductile or tough materials, and fiber materials can be the stiff or stronger materials with lightweight, and also the fiber or reinforced materials can be formed in fiber, viscous or particulate material. Today we will focus on the carbon fiber, continuous fiber, polymer matrix composites. They have also many applications in aerospace, energy application, and automobile sector. And the carbon fiber materials, we choose the carbon fiber materials because the carbon fiber materials most stiffer and stronger than the glass fiber and aramid fiber composites. And they also 5 times lighter and 7 times stronger than the aluminum. Therefore, they found in greater place the usage in the aircraft structures. Here, some of the samples produced from the glass fiber, carbon fiber, and aramid fiber, and also the honeycomb core materials. All of them are using in the aircraft structures. The composite materials have found the many places in using the composite materials in aircraft structures, especially in their flying surfaces, fuselage beam flows, and also the control surfaces, flying control surfaces, and landing gear doors. And today, composite materials are used in new generation composites, especially in the Boeing 787. Here we give the example. This aircraft includes more than 50% of the carbon fiber and other composite materials, and also provides the weight reduction 20%. So the usage of the composite materials in aircraft structures provides commercial advantages like a low fuel consumption, and also due to their low weight, and also the reducing cost of bolts, because it needs a few of the bolts for assembly, like that. And there is some advantages these composite materials over the alloys. For example, they have a high corrosion and fatigue resistance. It means that also the fatigue resistance is also the commercial advantages for aircraft structures. High specific strength and stiffness. This is the important, because over the metal alloys, they have a high specific strength and stiffness, and lower thermal expansion coefficient. However, they have some disadvantages, especially needs for some applications. Lower conductivities, electrical and thermal conductivities. The poor conductivity of the carbon fiber composite materials has a poor conductivity. Therefore, they prone to the damage from the lightning strike. Therefore, it needs to be improve their conductivity properties. Here, some examples given in lightning strike damage from the aircraft. Boeing and Airbus company are used thin metal meshes, copper or aluminum meshes, to attach the carbon layer to improve the conductivity of the composite materials, to prone conductivity to composite materials. And also here we list some materials which is promising for lightning strike protection, promising materials. Copper and aluminum is generally used for lightning strike protection for aircraft structures. However, some scientists found that the aluminum has some drawbacks, because when the aluminum is connected with the carbon fiber materials, it has probably it occurred, galvanic corrosion is occurred, and copper is an alternative material compared with the aluminum, but the use of the copper make heavier the aircraft. That means that the higher fuel consumption. And in this table, silver can be used for conductive materials for lightning strike protection. However, this material is very expensive. Nowadays, some fillers like carbon-based materials are used for the filler materials to improve the carbon composites, carbon fiber composites conductivity for lightning strike. Here we can see the electrical conductivity values of the, especially graphene is higher than the metal materials, and therefore for the next 10 years these materials will be more popular, and the conductive to produce the conductive composite materials to stop the lightning strike protection and the galvanic corrosion, and provide the low fuel consumption. It provides many advantages. Another application of the conductive composite materials for de-icing application. Here we can see the heater mat. This is the real things. Real material is used in the aircrafts for dissipate the heating for de-icing applications. In aircraft, a very thin brass material was used in the outer surfaces of the over the composite structures, and the conductive rubber was covered on that. However, the brass materials has some disadvantages like oxidative corrosion. Therefore, if we use the conductive materials and we added the conductive materials within the epoxy or resin for carbon fiber composite, we improve their or enhance their conductivity to replace these conductive materials with the metal mesh or some heater elements used in aircrafts now. Here, some example from the literature. Here, the graphene was added to polyether ketone resin to improve their thermal properties of the composites. The phonon connection and the heating dissipation is increased when using the graphene in this material. This is an example for what I mentioned about the conductive composite materials. To achieve the well properties like a good performance of the composite materials for aircraft structure. The distribution or preparation of the epoxy graphene dispersion is crucial role. Therefore, in order to disperse the graphene within the epoxy matrix, there are lots of processing techniques like 3-roll mill, ball milling, shear milling. They are used generally with the together with the ultrasonic homogenizer. Another techniques to improve the conductivity of carbon-based or glass fiber-based composite materials, the coating of the surface of layers, carbon layers, or coating the single fibers surfaces with the conductive materials. These are the electrophoretic deposition, dip coating, or carbon fiber coating process. After that, or spray coating that we use in our some of the experiments. The carbon fiber coated with the after the coating with the graphene can be seen from this SEM images. Now we produced 4 different conductive carbon fiber composite materials. In the first experiments, we used the commercial graphene and mixed with the epoxy using the sonication technique. We used 8 plies of the carbon fiber fabric. Here is some data belongs to the commercial graphene. In this second experiments, we also joint work with the Professor Felipe, and we produced the carbon fiber reinforced reduced graphene oxides epoxy composites. Reduced graphene oxide was supplied from the Professor Felipe. They are produced this reduced graphene oxide using the astaxanthin. After that, we add this reduced graphene oxide using the shear mixer and also the sonication. We also modified the reduced graphene oxide using the polyvinyl fluoride, because the polyvinyl fluoride, polyvinyl propylene, PVP, provides the better distribution of the graphene within the epoxy matrix. So we prepared the 2 groups of composites. One is without PVP, and the other is with PVP. Here is some data belongs to the reduced graphene oxide samples. And also we can see from here the without PVP and with PVP the distribution of the graphene. And the last experiments, we in our laboratory we produced the silver reduced graphene oxides powders, and using the we use the ascorbic acid as a reduce the graphene oxide, and we mix the using shear mixer, and also this mission is exfoliate the graphene within the to mixing the also exfoliate the graphene oxide within the epoxy. And then we use the also the sonication technique under the cold tub. And we sprayed the solution, including the silver reduced graphene oxide and alcohol, ethyl alcohol solution onto the carbon fiber layer. And then all of the composites were produced using the vacuum infusion technique. This is the schematic view of this process. And also after the fabrication, you can see from this picture the composites. We use the 8-ply of the carbon fabric using the flat glass surfaces coated with the Teflon-based material. And then we infused the epoxy mixing with the graphene using the vacuum pump after the sealing the surface of the plies. And we can see here from here with and without graphene the ACM images of the P-ply material with and without the graphene oxide, graphene nanoparticles. After produce the composite materials, we measure also the surface and through the thickness conductivity, through the layer conductivity of the samples using the Kitley resistivity text fixture and the source meter. Our results is comparable in this table, comparable with the results taken from the literature. So, and in the if we also produce the control sample, or need sample, the name is need sample, to compare the conductivity results with graphene or silver reduced graphene containing the composite materials. If we compare with the carbon fiber composites with the graphene added carbon fiber composites, 1.25 weight percent of graphene when we add the 1.25 weight percent graphene to the carbon fiber composites, 100% increase was observed. When we add the silver reduced graphene oxide, 0.45 weight percent into the carbon fiber composites, the conductivity of samples increases 200% when we compare with the need or control samples. Here we can also see the reduced graphene oxides reduced with the astaxanthin samples with PVP modified and without PVP samples. In the same filler amount, we can see from here the PVP containing reduced graphene oxide carbon fiber samples show a higher conductivity results. These results can be comparable with the literature, and we can see from the different conductivity results. because the conductivity of these samples can be changed using the applying, depending of the applying process and the amount of the graphene and also the quality of the graphene. Therefore, the differences coming from these factors. We also measured the dynamic mechanical analysis of these samples. Dynamic mechanical analysis gives some this is the useful tool for measure the viscoelastic properties of the materials under the different loading conditions. We use the 3-point bending mode in this in all composite samples under this constant frequency as a function of the temperature. Here we can see the commercial graphene containing samples storage modulus. The storage modulus is measured from the obtained from the dynamic mechanical analysis system. The storage modulus gives the stiffness of gives some information about the stiffness of the materials and the energy storage during the deformation about those in elastic manner of the samples. Here we can see that the storage modulus does not depend on the amount of the graphene, the amount of the graphene. Only we see that the higher stiffness value compared with the neat composite or contour composites, we obtain only the higher stiffness for 0.05 weight percent composite graphene containing composite materials. This is probably due to the fabrication process, production process of the or distribution process of the graphene within the epoxy, since we only use the sonication technique in these samples. And also the story in this picture, the graphic, we also see the storage modulus belongs to the PVP modified and unmodified samples. Here we can see the differences when we use the PVP as a modifier for graphene. This is, we can see from here the stiffness of the materials, composite materials, is increased with using the PVP, since the PVP provides the better distribution of the graphene within the epoxy matrix. And also we can see different from the before slides. We can see here from that the increasing the amount of reduced graphene oxides, the storage modulus of also the increases. This can be attributed to the presence of the reduced graphene oxide within the epoxy matrix, restrict the motion of the epoxy, motion of the polymer chains, and increase the load bearing capacity of these samples. We also look at the flexural strength of the composite materials. We can see from here the flexural stress and strain belongs to the commercial graphene containing the samples. Here, after the maximum stress, all of the composite materials containing the graphene shows a drop decrease in flexural stress. This may be this probably due to the fiber breakage in those samples. You also see this phenomena in the SEM images. And you can see.
Kaftelen, time is over.
Okay, I will finish as soon as. Flexural strand also does not so much change with the addition of the graphene within the composite materials. And another samples containing the silver graphene samples shows the similar results with the commercial one. The flexural strands almost the same without any decreasing. After the 0.45 samples, 45 addition of the silver graphene samples, the flexural strength is reduced. This may be due to the agglomeration of these powders within the epoxy matrix. Now we can see the fracture surfaces of the samples. Here, the neat samples shows the delamination, and the other composite samples shows the fiber breakage that I mentioned before. And lastly, we can see in the neat composite, the bare surfaces of the fiber. There is a very smooth surface. And in the composites containing 0.05 graphene, there is a strong connection between the fiber materials. And the last picture from the fiber, we can see also the graphene within the surface of the fibers. In summary, we obtained 136% increase through the thickness of electrical conductivity of the laminates was observed with the modifying the PVP of the samples. In general, the change in mechanical properties of graphene-added composite laminates relative to the neat composites can be considered insignificant because when we compare to the substantial improvements noted through the thickness of electrical conductivity. So the many factors, including the quality of graphene concentration, mixing process with also the polymer matrix, modification of the graphene particle stability in graphene dispersion, in constituent interfaces contributed to the differences observed in the mechanical and physical properties of the composites. These are the references. You can contact me if you have a further question. Thank you so much for your attention.
Thank you, Doctora Kaftelen. Now is question time. Bien, gracias a la doctora Kaftelen por su interesante presentación. Si acaso damos tiempo a una pregunta. Si alguien, una sola pregunta. Only one question. No? There are no questions. No hay preguntas. Bien. Gracias a la doctora Kaftelen por su participación.
Thank you, it is a pleasure.
Thank you, doctora Kaftelen.
It is a pleasure for me, thank you.
Esperamos contar con su participación. Bien, vamos a continuar con nuestra siguiente participación. We will continue with the next participation. The turn is for Dr. Palania Nagarajan from Indian Institute of Technology. Le damos ahora el lugar al doctor Palaniappan del Instituto Tecnológico de la India. Esperamos a que comparta su pantalla. Doctor Palaniappan, good afternoon. We can see your screen, but not your presentation.
Hello? Yes. Good morning, ma'am. Listening, ma'am. My voice is coming. Hello?
Yeah, we can see your screen, but not your presentation. Only
Okay.
the Explorer.
Okay, now is sharing my slides are coming.
Yeah.
Okay. Now my slides are visible. My slides are sharing now. Now visible.
No, not visible your slide. See the file Explorer.
Slides. No, ma'am. Now slides